Welcome all for the session Registers and Counters, which is third unit of Digital Electronics, third semester. In this session, we are going to learn about definition of a counter, types of counter, classification of counters, and working of 2-bit asynchronous counter. At the end of the session, we will have the small multiple choice questions test or quiz. Then what we are going to learn at the end of the session, you will acquire definition of the counter, classification of the counters or different types of the counters, and explain the working of one 2-bit asynchronous counter. Let us study one by one. Counter. What is a counter? A counter is a device which stores and sometimes displays the number of times a particular event or process has occurred, or a digital circuit which is used for counting pulses is known as count. For example, a binary counter counts from 0 to 2 power n minus 1, where n is the number of bits or flip-flops in the counter. For example, for 2-bit counter, it counts up to 3. That is, because of 2 power n times the binary numbers progress from 0. That is 0 to 2 power 2 is equal to 4. Because 0 is also one number considered, it always counts one number less. That is 2 power 2 is equal to 4 minus 1 is equal to 3. It always counts from 0 to 3. That is 0 0, 0 1, 1 0 and 1 1. If it is 3-bit counter, it counts 0 to 7. That is 2 power 3 is equal to 8 minus 1 is equal to 7. Okay, where do you find these counters, digital counters? We know that nowadays the world is digital. Everywhere we use the digital systems. In your mobile also we have the timer, counter also. And in general we use the digital clock. Our wristwatches or wall clock also we use the counter to count the minutes, hours and seconds also. Sometimes we can also use to display the temperature, pressure, whatever it is. So many applications are there. And also you can find, you might have seen in the bank to count the currency machines. And also you might have seen in the bike, car, everywhere you have the counter to measure the speed of the vehicles or RPM measurement. Then also in process or product management, how many items that is passing through the and passing over the conveyor belt is also we can measure. That is, you can see another progress. So many applications are there to counter. Then you have seen some definitions. That is what you call the modulus of counter. Now what is the modulus of counter? The number of different output states a counter can produce is called the modulo or modulus of the counter. See, for a binary counter, it always counts from 0 to 2 power n minus 1, 2 power n minus 1 times. Sometimes you don't want to count the entire counter. We can skip number of counts. So it is called modulo. How many numbers that it counts is called a modulo. That is, modulo of a counter is the total number of unique states it passes through in one complete counting cycle. If we count to the complete counting cycle, the 2-bit counter counts 0 to 3, 3-bit counts 0 to 7. If you don't want to count the entire cycle, we can skip the upper number of bits or a lower number of bits. That is requirement of our applications. That is called modulo counter. Mod n counter being described as a divide by n counter. Generally we use this counter circuit sometimes in the digital circuits as a frequency divider. Used as a frequency divider where mod number is equal to 2 power n. That means if you use the 3-bit counter, 2 power 3 is equal to 8. That means it divides the input frequency by 8 times. That is also an application. For example, here is also see some examples. That is a mod 5 counter, means it counts 0, 1, 2, 3, 4 and returns to 0. The 2-bit ripple counter is also called as mod 4 counter. That is, it counts 0, 1, 2, 3 and returns 0. A 3-bit ripple counter, as I said, it counts up to 8. So in general, an n-bit ripple counter is also called modulo n counter. where mod number is equal to 2 power n. Then mod counter types. How many types are there in mod counter? Two types. One is full mod counter. In the full mod counter, the binary counter progress from 0 to the maximum count, that is 2 power n minus 1 times. That is called full mod counter. Another one is partial mod counter. In partial mod counter, we can skip the some output states and terminate to the predefined state is called the partial mod counter. The partial mod counter output is nothing but is generally called as a terminal of a counter. Now we will study the classification of the counters. Okay, we have the various types of the counters, and based on the depends on the parameter that you are applied, we are going to classify the counters depending on the applications of the clock. The counter is classified as asynchronous counter. In asynchronous counter, when counter is connected cascading up the flip-flops. When the first flip-flop is applied the clock pulse, the subsequent flip-flop is triggered by the output of the previous flip-flop. Clock is not applied to all the flip-flops. The clock pulse is applied only to the first flip-flop, and the remaining flip-flops are triggered by the output of the previous flip-flop. Hence, all flip-flops do not change their state at the same time. That is called asynchronous counter. And second one is synchronous counter. In synchronous counter, the clock pulse is applied to all the flip-flops simultaneously. So all flip-flops are triggered or produce the output at the same time. That is called synchronous counter. Next, depending on the direction of the counting, counters are two types. Up counter. A counter counts from 0 to maximum value in the incremented way. It is called up counter. A counter counts from the maximum value to the 0 towards 0, counting from up maximum value to the 0 value is called a down counter. And depends on the modulus of the counter. There are also two types. One is binary counter. Binary counter, as I said, it counts from 0 to maximum value. The binary counter passes through all the possible states before returning to the initial state. It is full modulus counter. Mod n counter. It is a counter in which the maximum number of states can be changed. The final state of a count is called as terminal count. Depends on the application. We can use the binary counter or mod n counter. Then you study the one by one counters. Now we will study the asynchronous counter. What is asynchronous counter? In an asynchronous counter, the clock pulse is not applied to all the flip-flops. The clock pulse is applied only to the first flip-flop, and the succeeding flip-flops are triggered by the output of the previous flip-flop. Hence, all flip-flops do not change their state at the same time, because the succeeding flip-flop depends on the output of the previous flip-flops. So, merits. What is the merits of the asynchronous counter? Simple design, because output is given to the succeeding flip-flop in clock input, and the next succeeding flip-flop gets the clock from the output of the previous flip-flop. So it is a simple design. Requires less hardware. We do not require any much additional hardware for the performance, and easy operation, low cost, because it do not require any much hardware. The cost is also less. What is the demerits of this asynchronous counter? Slower in speed, because the succeeding number of states go on increases in the flip-flops. Okay, the speed is decreases because the response time is very less, because it gets the clock from the previous flip-flop only. So it is a lesser speed. When number of stages increases, the propagation delay increases. That is the demerits of asynchronous counter. Now let us study one by one. Then to study this one, what is the prerequisite that you can understand that is required for this preparation of the asynchronous counter? Asynchronous counter. What is the prerequisite that is required to construct the asynchronous counter? We need flip-flops. What are the flip-flops that we require? JK flip-flop or T flip-flops or inverted D flip-flops. We will study one by one the basic function of these flip-flop. See, already you might have known about these flip-flops. You have already studied in the previous classes about these flip-flops. flip-flops. See, let us study the JK flip-flop. Recap of that one. Okay, it has two inputs, J and K, and Q and Q bar. This is a truth table of JK flip-flop. When J and K flip-flop is equal to 0, there is no change in the output. That is Q remain Q only. When J is equal to 0, K is equal to 1, it is reset. Okay, it becomes 0. Reset means it is 0. When J is equal to 1 and K is equal to 0, then it is set. When J and K is equal to 1, it is toggle. It is toggle. For our applications, this toggling condition is required. For our application, this toggling condition is required. Because in counter, it is always changes from states. Let us see here. Okay, counter always changes states from 0, 0, 0, 1, 1, 0, 1, 1, again 0, 0. In binary counter, it always changes states from 0, 1, 0, 1, 0, 1, so on. Or 0, 0, 1, 1, 0, 0, 1, 1. Continuously the state is changing. So we require a toggling condition here. JK flip-flop, to make it as a counter, we must use J is equal to 1 and K is equal to 1. Then this state will be used. So we have to make this J and K. We have to make this J and K is equal to 1 or J is equal to K 1 or I is equal to 1. Then another flip-flop is called T flip-flop. The T flip-flop is modified version of the JK flip-flop. So just connect this T and J, short this T and J. Sorry, J and K. Then it will become T is equal to 1. So when J and K is shorted, then only two conditions exist, that is 0, 0 or 1, 1 condition exists. Then when T is equal to 0, that is J and K is equal to 0, that is no change. That we don't want. When T is equal to 1, that is J is equal to 1, K is equal to 1, that is J is equal to 1 and K is equal to 1, that is toggle condition. So for JK flip-flop, we can modify, make it as a T flip-flop by shortening the J and K. In D flip-flop, the inverted output of the D flip-flop is given back to the D. So for every time, the input to the D flip-flop is continuously changing. Here is 1. When clock pulse is applied, is also a 1 here. 1. When clock pulse is applied, the 1 appears at the output. When Q is equal to 1, automatically Q bar is equal to 0. Again this 0 is applied to the again the input of the D flip-flop. Again clock pulse is applied, input is D, the output is also D. When Q is equal to Q is equal to 0, then Q bar is equal to 1. See, continuously for every clock pulse, it is also go on toggling here. So the D flip-flop can be also acts as a JK or another T flip-flop here. But generally we do not use much about the D flip-flop for application. D flip-flop will be used for only the registers applications. We prefer JK flip-flop over all other flip-flop frequently. Sometimes we also use the T flip-flops here. Now let us study the 2-bit flip-flop, that is asynchronous counter. Okay, asynchronous counter here. Asynchronous counter here. See, in 2-bit asynchronous counter, here we use the JK flip-flop. Used here JK flip-flop. See, the JK flip-flop, to make it as a counter, as I told, the J input here, J input and K input is shorted and connected to the I, that means it is 1. And here is also J and K is connected, shorted and connected to the I input, that is binary 1. As I told in the asynchronous counter, the output of the previous flip-flop is given to the clock pulse to the next flip-flop. The first flip-flop is only driven by the clock. This inverted bits indicate that this is the negative edged, negative triggering flip-flop. We know that there is a 4 types of triggering. We know that we have 4 types of triggering, that is positive edge triggering, another one is negative edge triggering, next positive level sensitive and negative level sensitives. For flip-flops, either we use positive edge or use the negative edge triggering here. Here it is a negative edge triggering. That means this flip-flop responds or changes its states only during the falling edge of the clock pulse. Only during the falling edge of the clock pulse here. Because it is a negative edge triggering. Now see the working of this flip-flop. Now see the working of this flip-flop here. How does it work here? Initially it is reset. This is a clear pin. It is a clear pin that you are connected here. Initially it is reset is equal to 1. Okay, it is a reset initially. When flip-flop is clear, that is output of the flip-flop is QA, that is QA is equal to 0 and QB is equal to 0. The output, that is QA and QB both. QA is equal to 0 here. When first clock pulse applied, when first clock pulse is applied, it goes to the high. When it goes to the low, 1 clock pulse is applied. During the falling edge of the first clock pulse, the output changes. Because JK flip-flop, the input is tied to high, it is always toggles for every clock pulse. So it is, when first clock pulse is applied, it goes to the 0 to 1. It goes to the 0 to 1. At the same time, it goes to the 0 to 1 state, 0 to 1 state here. When it goes to the 0 to 1 state, it do not feel it as a clock because it is a negative edge triggering. It always feel it as a clock only when it has to flow from 1 to 0. Then it goes to the 0 to 1 and stays high again. During the next clock period, second clock period, when it goes to the 1 to 0, second clock pulse, when it goes to the 1 to 0, second clock pulse, then the output is 1 already here. Output is 1. During the second clock pulse, the output 1, it goes to the 0. The output is 1, it goes to the 0 state. At the same time, when it goes to the 1 to 0 state, this flip-flop feel that it is a clock because it goes to the 1 to 0. This flip-flop, it feels as a clock, that is negative edge triggering clock. So it also changes its state 0 to 1 because earlier it is 0, here is also 0 because no change. Now it goes to the 0 to 1. When third clock is applied, during the negative edge of the third clock pulse is applied, during this period time, then again the flip-flop status changes from 0 to 1. Changes its states from 0 to 1. When it changes states from 0 to 1, there is no change in the second flip-flop, that is flip-flop B, because it do not respond. It always responds only from 1 to 0. So it stays I for remaining states. That is only 1. Again this clock is also 1. When the fourth clock pulse is applied, when the fourth clock pulse is applied, this flip-flop is 1. When this clock is applied, it becomes 0. When clock is applied, it becomes 0. When clock is applied, it becomes 0. When it goes to the 1 to 0, then this flip-flop, second flip-flop, feels it as a clock. Then the second flip-flop is also goes 1 to 0 because the previous state is 1. Automatically changes its states, then it becomes 1 to 0. So both are stays high. During the fifth flip-flop, again 0 to 0. When fifth clock pulse is applied, again it goes 1 to 0, 0 to 1, again it remains as high. In this fashion, the 2-bit asynchronous counter is working. In the 2-bit asynchronous counter, we table the values, that is 0, 0, 0, 0, that is 1, 0, first class frequency, that is 1, 0, second clock cycle 0 1, that is 0 1, that is 1 1, that is 1 1, third clock cycle. Again in the fourth cycle it goes to the 0 0, that is 0 0. In the fifth clock cycle it repeats again, the cycle is continuously repeats again here. Okay, that is the working of the asynchronous counter. Next to see something. Okay, what are the possible questions that you may get here? Okay, you may get questions. Define counter. Counters based on clocking, direction of counting and modulus. You may also get the question, construct and explain the working of 2-bit asynchronous up or down counter. Then calculate the number of flip-flops required to construct a counter that counts from 0 to 29. That you have to calculate. How many flip-flops are needed to construct the counter which counts from 0 to 29? Such questions you may get in the examinations. See here we asked working of 2-bit up counter or 2-bit down counter. What to do to construct the 2-bit down counter here? Instead of taking the outputs here, instead of taking the outputs from Q and Q bar, instead of taking the outputs from Q and Q bar, you take the output from Q bar. Take that from Q bar, that is Q0 bar and Q1 bar. Then it acts as a down counter. Okay, same circuit, you take the output from Q0 and Q bar. So you can see very easy. When Q0 and 0 0, it becomes a 1 1. When it is 0 1, it becomes a 1 1 0. When it is 1 0, it becomes a 0 1. When it is 1 1, it becomes a 0 0, because it is the opposite state. That is, you can see 3 2 1 0. Just to take the output of the opposite, that is Q bar, you will get a down counter here. That is it. Okay, some multiple choice questions that you can see. Okay, recap of that one. In digital logic, a counter is a device which counts the number of outputs, stores the number of times a particular event or process has occurred, stores the number of times a clock pulse rises and falls, count the number of inputs. Which one? C. Stores the number of times a particular event or process has occurred. Okay, answer is B. Second question. A counter circuit is usually constructed of ಯಾತ್ರಿಂದ ಕೌಂಟರ್ ಸರ್ಕ್ಯೂಟ್ನ ಕನ್ಸ್ಟ್ರಕ್ಟ್ ಮಾಡ್ತೀವಿ? ಲ್ಯಾಚಸ್ ಇಂದ, ನ್ಯಾಂಡ್ ಗೇಟ್ ಇಂದ, ಫ್ಲಿಪ್ ಫ್ಲಾಪ್ಸ್ ಇಂದ ಆರ್ ನಾರ್ ಗೇಟ್ ಇಂದ. We construct the counter using flip flops. Answer C, because we cannot construct the counter using NAND gate or latches or NOR gates here. Okay, third question. What is the maximum possible range of bit count, specifically in n-bit binary counter consisting of n number of flip flops? 0 to 2 power n times, 0 to 2 power n plus 1 times, 0 to 2 power n minus 1 times, 0 to 2 power n plus 1 by 2 times. Okay, the binary counter is always counts from 0 to 2 power n minus 1 times. That is, answer is C. Next, these are some references that you go through here. Okay, this is our digital electronics team who have contributed for this session. Okay, thank you.